Welcome to another episode of Progress, Potential, and Possibilities, discussions with fascinating people designing a better tomorrow for all of us. I'm your host, Ira Pastor.
Welcome, everybody, again to another episode of our show. Today, bringing you another really awesome guest involved in creating a better tomorrow for so many people out there. Today, we have the honor of being joined by Dr. Behnaam Aazhang, who is the J.S. Abercrombie Professor of Electrical and Computer Engineering, as well as Director of the Rice Neuroengineering Initiative at Rice University, where he has broad research interest, including in the areas of signal and data processing, information theory, dynamic systems, as well as all their applications to neuroengineering. And with this portfolio, his organization focuses in areas like understanding neuronal circuit connectivity, the impact of learning on connectivity. They're involved in the development of a wide range of minimally invasive and non-invasive real-time closed-loop stimulation of neuronal systems, ultimately to help mitigate disorders like epilepsy, Parkinson's, depression, just to name a few. They're involved in developing patient-specific multi-site wireless monitoring and pacing systems to restore the healthy function of the diseased heart. And then also because of his long history in the computational space, they're involved in developing algorithms to detect, predict, prevent security breaches in various cloud computing and storage systems. Dr. Aazhang has his bachelor's, master's, and Ph.D. All in electrical and computer engineering from University of Illinois, Urbana-Champaign. From 1981 to 1985, he was a research assistant at this really interesting coordinated science laboratory at the University of Illinois, where he did his Ph.D., joined Rice University back in 1985. And then in addition to all that work from 2006 to 2014, he also held an Academy of Finland Distinguished Visiting Professorship at University of Oulu in Finland. Dr. Aazhang is a fellow of both the Institute of Electrical and Electronics Engineers, as well as the American Association for Advancement of Science, a distinguished lecturer of the Institute of Electrical and Electronics Engineers as well. Widely published across a range of these topics. A lot of really interesting themes to get into today. We're honored to have him with us. Dr. Behnaam Aazhang, thank you so much for taking the time to come on our show today.
It is a pleasure. Thank you for inviting me.
It's awesome having you. I've really been looking forward to this episode and sort of the wide range of stuff that you've been up to there at Rice. I would love to start off, though, because your story goes back a little way. It's been on a really interesting set of pathways. I'd love for you to take us back to the late 70s, early 80s. I was reading about you. You were studying in Iran. You leave Iran around 1979. You end up at University of Illinois at this really advanced, first time, this coordinated science laboratory, which not only is doing sort of very classified defense stuff, but a really interesting mix of public and private financiers on the cutting edge. Take us back to those days. Take us back to your Ph.D., performance of direct sequence, spread sequence, multiple access communications and impulsive channels, and everything that was going on at that time. I think that's a great way to set the stage for a lot of what we're going to be getting into.
Sounds great. I, grew up in Iran, and then I studied at a university there, a technical university nowadays called Sharif University of Technology. I'm sure you've heard of it. There are a lot of very, very strong students coming out of that university. And I came to US in the middle of the revolution. there, and I went to University of Illinois and finished up my degrees there, my bachelor's degrees, and then joined there as a PhD student. And as you said, I work inside the coordinated science lab, but as you said, there was classified work there and unclassified. Obviously, I did only unclassified work, and I worked with my PhD advisor, who is an incredibly nice person and incredibly accomplished. And then I worked in the wireless communication area and did interesting, hopefully interesting work that I really enjoyed. And then I landed this position at Rice, which was a very sort of intriguing position. And I came to Rice right after my PhD. And then I've been at Rice for now 38 years. And the first 20 plus years, I continued doing work in this area of wireless communication, and wireless communication as an area was very hot at the time because our devices and our communication system were getting developed, and I worked a lot with a company in Finland called Nokia, and then
Sure.
I did a lot of work in that space. And published a lot and all that, and had a lot of fun. And then 10 15 years ago or so, I decided to move out of that area because I felt like there was a lot done and it's time to look at some new applications. And I basically use the tools that I have been using for wireless communication to a new application space, and basically using signal processing and information theory and statistical analysis of signals to this new area that at the time we didn't know what to call it, and it's been a established area called neuroscience.
Mhm.
But then because we are all engineers, we decided to call it neuroengineering, basically, or neurotechnology. And same tools, but very, very different application. And it's been a blast. And as you may know, Rice University is literally across the street from the world's largest medical center, Texas Medical Center. And there are a whole bunch of neurosurgeons and neuroscientists and neurologists across the street. And then when we sort of got interested in this area, it was very, very easy to find a set of collaborators to work with and try to focus on, research areas that are relevant and they would help people, basically help patients and all that. And then it's been a real ride. And over the last 10 years or so, we have, were able to secure a lot of fundings from National Institute of Health, National Science Foundation, and Department of Defense, and all of that. And as you said, we've been working on all of these disorders and try to understand how learning works, how memory works, and all that. And then I had the, the opportunity and the pleasure to build a group at Rice. We call it Neuroengineering Initiative, and basically hired a number of incredible faculty. And now we're gonna have, by next year, we're gonna have 15 core faculty in this space. Whole bunch of engineers that are focusing on neuroscience, neurosurgery, and all that, and developing gadgets and tools. I'm going to stop and see if you have any questions.
No. It's as I was taking sort of that ride through, and for everybody listening and watching, if you want to go to Dr. Aazhang's Google Scholar or PubMed, it's extensive. But I was looking at actually started back in 1986, and you talk about yourself in a lot of presentations as initially the signals processing guy. You're publishing hundreds of papers in signals processing and multimedia communications, wireless, and all that. And then, as you were saying, in the early 2010s, papers on Parkinson's disease models, on epilepsy, on different ways to stimulate dopamine depletion in certain parts of animal brains, so forth. These papers start showing up. Talk a little bit about that intersection, as you were saying, obviously two different worlds. You got your silicon over here, which you're playing with for a couple decades. Now you're in the sort of the organic, wet and wild world of carbon. Yet both, these electrochemical systems that do interesting stuff, both sending signals and processing them and all that. Talk about the very early days of that. What were some of the, I guess, the early aha moments that said, hey, you know what? This makes sense. This could work. This isn't as different as I thought it might have been back in the early days when I was working on phones at Nokia or whatever.
Yeah. Well, I give a lot of credit to my colleagues. My colleagues in University of Texas Health Sciences, and nowadays Methodist Hospital and Baylor College of Medicine. Basically, we started a very interesting collaboration. As an example, my colleagues at UT Health were interested in epilepsy. That's what they did, and the question was, if we have electrodes that could be placed on the surface of the brain or underneath the skull, and we get a lot of signals, is it possible to predict seizure for an epileptic patient? That to me, that's an intriguing question. Sure. It's a question that has a lot of content, and the question is, can we get it done? And that was a challenge, and it turns out that we looked at that challenge, and it turns out that electrodes that record from the brain carry a lot of information, carry a lot of signals, and then because we were looking for patterns, let's say a patient has a couple of seizures a day, and the challenge that we faced was that if you know the history of the patient and you watch the patient having, let's say, 20 seizures in over a 10-day period, is it possible for us, from watching the signals and recording those signals, can we predict the next seizure? I think that would be a very useful challenge, that if we can solve it, and then that would enable the patients to pull their car to the side of the road. It enables them to brace themselves, and many other advantages that brings to the patients and improves patients' lives. And that problem is so you can think of it as a prediction problem, like it is similar to predicting earthquake, for instance. And that is also an interesting open problem. And we worked on that, and then we were able to secure funding, and we were able to sort of come up with algorithms that look at the history of the patient, and based on the 20 seizures that the patient had, can we predict the onset of the next seizure, 21st seizure. And we were able to publish that and all that. And this is a typical challenge that we face. And my colleague at UT Health, Dr. Nitin Tandon, is a surgeon, neurosurgeon, and he's been devoting his career on epilepsy, and he does tons of surgeries and all that. And we continued that work, and nowadays we are interested to see if there is a way that we could stimulate the brain instead of resecting the brain tissue, to see if we can mitigate the epileptic zone and not let the seizure to develop. Using stimulation as opposed to resection of the brain or ablation of that brain tissue, which I think is a very important problem, and this is something that we are working on today.
And one other place I want to stop before we get to Rice Neuroengineering Initiative is, again, you have a tremendous amount of fascinating papers here. This one was from 2015. I think it was ACS Nano. It was entitled Neural Stimulation and Recording with Bidirectional Soft Carbon Nanotube Fiber Microelectrodes. And I thought this was a really interesting paper, because it nicely sort of segues into what you've set up at Rice now in terms of the multidisciplinary convergent themes here. And you're pointing out in this paper that, look, and I think maybe today's social media world sort of has oversimplified a little bit about brain-computer interfaces, that, we're just going to plug something in and we're fine. No, you point out here, look, this is electrochemistry, this is material sciences, this is medicine, this is a wide range of other disciplines that got to work together, or else we're not going to have, as you were mentioning, to deal with whether it's epilepsy or Parkinson's, we're not going to have the perfect interventions. So we got to bring that team together. Talk a little bit about this paper, if you would, in 2015, and I promise you after that we'll segue to RNI.
Sure. Now, interesting because as you just said yourself, this area of neuroengineering is very broad. And then I think we can bring in folks that do material science. Yeah. We can bring in folks that could do signal processing, that could build experimental setup and all that. And I think in that particular paper, we collaborated with a very good friend of ours, a professor in chemical engineering department at Rice, that has built a career around the concept of carbon nanotubes. And carbon nanotubes are, and that particular idea was invasive. Therefore, you insert a carbon nanotube, which are not they're not like big electrodes. They're very small. And then you can think of it as being invasive, obviously, but it doesn't damage the brain tissues. Right. That was the whole idea. And then the question is, can we interface with the brain? And if possible, can we stimulate the brain using that technology? And in that particular paper, we looked at that particular problem with my colleague and a couple of postdocs and all that. And it was a very well-received paper, and it opened up a lot of doors and brought in colleagues of ours in material science area, and you basically help them develop technologies from material science to solve the interface with the brain, the issue of how to interface with the brain without damaging neurons and damaging brain tissues, which is still an open problem. And as a result of topics like that, we were able to hire, right now we are bringing in 2 colleagues that are pure material scientists, and they develop materials like polymers and other materials, soft materials, with a lot of recording possibility, thousands of channels of recording, to Rice, to our NEI, and work with them to see what they can put together in terms of materials that you could place it inside the brain for years, not just for a week, to record over a long period without damaging and without the electrodes losing their capability to record. Basically, what happened before was that electrodes would be placed, and after a week, your brain would basically, in a subtle way, attack the electrodes. Sure. And reduce their capability to record, and that's not good. And then the question is that, can we build materials that could last inside the brain tissue for years? That is a very important problem that my colleagues are attacking. I am not a material scientist, by the way, but I like to work with them and try to understand and try to develop a very much of a multi-channel that would have thousands of channels that you could insert in the brain tissue and be able to leave it there and then record for months and years.
And again, this speaks to the multidisciplinary structure of what you've now put together at Rice Neuroengineering Initiative. You set it up back, I believe, in 2018, and forgive me, I see the parallels between this and obviously the Coordinated Science Lab from a couple of decades ago. But you have the neuroscientists, the engineers. You're right there at Texas Medical Center, and then you got obviously some great funding partners here, not just groups like NIH and NSF, but you have DARPA there. I had, a couple of years ago, I had Alamondi on when he was still at DARPA working on sort of the haptics program there. So some, obviously funders that see the short and sort of the longer term vision here. take us into what it was like setting this all up. Obviously, you successfully put it together. Talk a little bit about that process. Obviously, the raising of funds for it. Walk us through a little of that sort of that 2018 period when you put all this together.
Again, I would like to give credit to my president. Rice University's president had a vision that Rice is very strong in engineering. And across the street, we got the world's largest medical center with no engineering, obviously, because they are a medical center, right? And the question is, can we as engineers work with them and build this basic initiative that would have a vision? The vision is to understand how the brain works, and to sort of, when the brain is not healthy, how can we move it from an unhealthy state to a healthy state, using technologies and stimulations and modulation, other technologies. And our president at the time and our president today are committed to this vision, are committed to this initiative. And I was able to hire faculty. That's it. And I got lucky, and I was able to hire some superstars to come to Rice and explore the opportunities at the medical center, and explore opportunities within Rice, and build what we have built today. And I've been very fortunate to be able to hire superstars. And then when you hire superstars, then you attract other superstars. The next thing you know, you have a group of 10, 15 faculty around you that could attack and work on a number of different problems. And that's what we have today. And you've seen the list, you've seen their pictures and all that. They're all, sort of incredibly active, incredibly successful in their own adventures. And as you said, it is a very interdisciplinary area. We have people that are very experimentalists, and we have people like me that are not. But we work together, and we are putting together ideas from the computational part, to signal processing part, to experimental part, to material science aspects of this problem, and then also the area of haptic and how to sort of help patients who had stroke and then they lost the functionality of their arm. What can we do to intervene in that functionality and all that? I mean, it's a very, very broad set of people, and funding is there. And it's one of the things that we should mention, as you know, a research group at a place like Rice relies heavily on strong graduate students. Sure. Therefore, the ones who do the actual work are graduate students. And it turns out that it has been very easy for us to attract superstar graduate students, because when you meet a graduate student and you talk to them about what research you're doing and how your research can help people, and how your research can help epileptic patients or a patient with a stroke and all that, it's a very strong selling point. And we've been able to bring a very strong set of graduate students, and that's how the whole engine works. Faculty, graduate student, postdocs, and funding and publication. This is the whole circle.
Let's dive into a couple of these projects, because again, and we'll put the link to the website in the bio of the show, and you have a broad portfolio here, and I picked a few out here just because they're kind of diverse and touch on themes that we've gotten into a bit on the show. But I really wanted to show the sort of the diversity of what you're doing here, because a lot of this sort of BCI work isn't just sort of the brain itself, but sort of the microenvironment, everything else going on. And I thought an interesting project to start with would be this work that you have going on in terms of the detection and restoration of glymphatic fluid flow, because this is obviously something, well, I guess it's been around for millions of years, but it's only sort of one of those sort of waste clearance systems that we've begun focusing on. We actually chatted about it about a year ago on another show in terms of more invasive processes on how you could potentially go in and drain some of the slowed or gunked up glymphatic system for applications in dementia. You point out here in your work that it may be possible via the technologies that you developed in your team to modulate glymphatic flow without drilling into the skull and leaking stuff out. And this has a wide range, as you point out, from traumatic brain injuries to Alzheimer's to even improving sleep, something I could use. Talk a little bit about your work on this particular work.
I am obsessed. I'm obsessed, and I like this area a lot. I honestly did not know much about glymphatic system maybe 5 years ago, and I learned along the way. And what I learned, as you just said, is that our brain has waste. I mean, so does every other organ in our body. And the question is, because of the blood-brain barrier, the usual, sort of oxygenation and other ways of cleaning up waste does not exist for our brain. And the lymphatic system that the rest of our body uses to get rid of waste, our brain does not have that. But instead, it has another mechanism that is similar to lymphatic flow, and it connects to lymphatic flow. And this is called glymphatic flow, and also that it is integrated very well with the cerebral spinal fluid flow. Basically, it is a flow of fluid, liquid throughout your brain. And this is sort of a very interesting, fascinating area to look at. And we've been looking at it for a while. And the question is, how do you measure the amount of the flow? How do you measure if you have enough flow and your brain is naturally cleaning up its waste? And it turns out that to get a good measurement of the glymphatic flow, you have to use MRI machine, magnetic resonance imaging machine, and it has to be phase contrast MRI, and it has to be 7 Tesla SRI. That means that it has to have enough resolution to be able to look at the changes of the phase, so that you could correlate that and learn from that the speed and the velocity and in the dimension of the surface of the flow, so that you would get a measurement of the flow. And then you could imagine that if the flow is compared to a healthy person is low, then you know that this is not a good sign. That means that your brain is not clearing out its waste fast enough. And that has been sort of been an indicator of the potential onset of Alzheimer's and dementia, which is not good. The question is there anything that we could do today to measure the glymphatic flow, and if it is low, alert the patient and be able to find ways to enhance the flow? Now, a 7 Tesla MRI is not readily available, and it needs an operator and all that. And the question is that, are there other modalities that we could use to measure the flow and correlate that measurement to a 7 Tesla MRI and be confident of our measurement? And then if the measurement tells you that the flow is low, is there anything you can do to enhance the flow? That is the challenge that we face. And it turns out that we were able, just a few months ago, we were able to investigate a number of different modalities and see whether we can learn from this, the recording of these modalities, and relate that to glymphatic flow. It turns out that we can. And the modalities that we tested were all non-invasive, and they were all very, very easy to implement. And we are calling this sort of prototype that we are putting together sleeping cap. Basically, that's a kind of cool term that one of our students came up with. Sleeping cap, basically you put the cap on your head, and it has a number of different electrodes that would basically do an EEG on you and record from, let's say, 16 different locations on the surface of the brain without being invasive. And from those signals, and from your EKG signals, and from your other modalities, can we learn enough from each of them and integrate the learning to see whether we can estimate the glymphatic flow? And we've been able to, and this is very much right out of the oven, and it is sort of, to me, is interesting and fascinating. And then, and it doesn't require any operator, doesn't require fancy MRI machines and all that. And then you can learn your flow. And then if your flow is low, then you could start thinking about what to do to enhance the flow.
Mm-hmm.
Now,
mm-hmm.
That is the measurement part. The modulation part is that we are working on another set of technologies that non-invasively can modulate your brain, and very, very focal modulation that we believe that is going to enhance your glymphatic flow. And we have done some simulations of that. We have done some biophysical simulations of that. And the next big step for us is to do that thing in an animal model.
Mm-hmm.
Basically, do the modulation in an animal model, try to enhance the glymphatic flow in an animal model like pig or primates or some other animal. It has to be a bigger animal model so that the electrodes, which are not invasive, they'll be placed on the surface of the brain. There is enough space to put the electrodes.
Mm-hmm. Mm-hmm.
I think if this works, this could be a step toward dealing with Alzheimer's. It would be a step toward dealing with dementia, and apparently a number of other disorders, not just Alzheimer's and dementia. Lack of clearance has been connected to a number of different disorders, not just Alzheimer's and dementia. In our opinion, that is a sort of a real game changer.
Yeah, absolutely. No, most definitely. I mean, obviously, there's if you solve Alzheimer's or dementia, or even, components or sort of the pieces of that, it's it changes everything. But yeah, I from past discussions about the glymphatic system, I clearly, that's why I wanted to bring that one up right away. But as we're on this theme of non-invasive health disorder, and then of course you mentioned sleeping cap, you also and out of the same technology but sort of related, you have this envelope technology related to obviously, I guess the way I think about what you've described here is sort of stimulating deep brain stimulation, which is becoming kind of hot for these neuropsychiatric disorders, but doing it non-invasively. And in envelope, it's sort of described as a little antenna array, sort of endocranially, not super invasive, but again, whether we're talking about depression or OCD or a list of other neuropsychiatric things, take us through it, because again, you not only are satisfying the non-invasive stuff here, but the as a signal processing person, the ability to get signal where it needs to go deep is important in these technologies. So walk us through envelope, if you would.
Yeah, I mean, again, the name is some of our students came up with that. I think is a cool little name that we put on that particular technology, and that is the exact technology that I was talking about with glymphatic flow. That is possible to use that technology. And if you think of the term non-invasive or invasive and all that, some people will say even taking a medication for epilepsy, for a number of these disorders is invasive, because you're taking medication that would have possibly side effects, right? Therefore, the term invasive, non-invasive, and minimally invasive, they basically have a range. And what is really non-invasive, what is really minimally invasive, all could be debated. And this particular technology, it is what it is. It is basically sends a beam, electromagnetic beam at a very high frequency through your skull and through your brain tissue. And these electromagnetic signals at the high frequency, we understand, and our simulations suggest that they do not interact with your neurons. Therefore, they go right through your neurons without interacting with your neurons.
Okay.
And which are basic signals, very much like your cell phone signals that they exist everywhere, and they possibly go through your skull and all that, right? Now, if you have two of these beams with a slightly different frequency, therefore their interaction, their intersection would be at a frequency that you could design so that that particular signal with that particular frequency will interact with your neurons. Therefore, you have a signal very focal and very small area that actually does interact with your neurons, and you could stimulate neurons, and that is the essence of this particular technology. And this idea of two signals interacting together to have a focality that would interact with your neuron is not our idea. It's been around for probably 10 years by now. It does our addition to that idea is the one that we use electromagnetic signals at high frequencies and a beam that very focal. And when it gets to this intersection, that is the one that at that particular low frequency interacts with your neurons. And we have done a whole bunch of simulations of this technology. We have done biophysical modeling of what it does to your neurons. And again, all we have left now to do would be to do it, to experiment in the animal models. Before we think about FDA, before we think about human applications. That's where we are today.
Excellent. Excellent.
Again, with all due modesty, I would say is a game changer. But again, I'm trying to be modest. But
these are all game changers, and that's why, again, why I was so, obviously I bothered you the last couple of years to come on the show, but clearly, every one of these is a game changer, and I just have to, this one other project that clearly, it's called the Rice Neuroengineering Initiative, but this has to do with the human heart. And clearly the heart and the brain have this very important relationship, both very interesting electrochemistry going on. I learned, I didn't know this, but I learned from sort of the work you're doing that as good as current pacemakers and resynchronization is, the ability to really in temporal and spatial preciseness in time and space to resynchronize hearts, we could be doing a lot better. And I'd love to hear a little bit how, again, a neuroengineering initiative with all its moonshots and game changers. I mean, this is clearly the biggest killer still on the planet, the diseased heart. What are you doing here? It's really cool.
Again, a very similar theme as a neuroengineering team. It's just that instead of the brain, we are focusing on the heart. As you said yourself, heart issues with heart and heart attack is still a #1 killer. And the question again is, how can engineers help, right?
Right.
How can engineers help in that particular space? As you know, pacemakers have been around for probably 20 years, I don't know. And sort of engineers have been, trying to help neuroscientists and neurosurgeons. Engineers have been trying to help cardiologists and all that. And we all agree with that. The question is, can we improve pacemakers? Can we basically develop technologies that synchronize, the blood flow and synchronize the muscles of the heart? As you know, there are 4 chambers, and these chambers, atrial, ventricle, and all that, they all have to right and left. They all have to work in synchrony to be able to have your heart function properly.
Right.
Again, we can record and record the pulses, record the movement of the electrical signals throughout the heart, and then learn whether the heart is functioning properly. And very focally and locally, we can stimulate to sync up the four chambers to work properly. And in that is that idea has been around for a while. We are not the inventors of this idea, but the question is that can we use modern electrodes, modern technologies in terms of machine learning, understanding the signal, and then making sure that the synchrony of these four chambers are perfect, as opposed to suboptimally, basically. And we can record, we can understand what the electrical patterns is, and then if we detect a poor conduction, we can intervene. The point today is that these pacemakers work 24/7, and the question is that needed, or can we selectively in time and selectively in space, in location, intervene? And hopefully the answer is yes. And the heart could be monitored in a very sort of global way, and then use the data and process the data and learn where to intervene. And a lot of times, cardiologists today, they go in and then they ablate. They find out where the electricity is misplaced or malfunction is, the function of it is poor, and they ablate that particular tissue. Is that needed, or can we avoid ablations? And they ablate in a number of different places till they find the right place that would help sync up the four chambers. Do we really need to ablate 14 locations to be able to find what's wrong and bring the heart to a functioning space? I don't think so. I think, and that's what we work with the cardiologist. And we're trying to understand by learning from the heart, where is the best place to ablate, or where is the best place to actually just pace as opposed to burn the tissue. Burning the tissue sounds like a last resort as opposed to first line of defense. Is it very different from brain? I don't think so. I think from my perspective, from perspective of a signal processing engineers, is there is a similarity in here.
It's a fascinating portfolio. I just have to ask while I have you, and if there's any confidential here, then obviously it doesn't say anything. But I saw the collaboration, I guess, from last year with the U.S. Army and sort of the glymphatic work in terms of ways to enhance sleep, and it got me thinking. A couple of years ago, I did a show with the folks from the Air Force Research Labs on something they're developing there called iNeurals, a way to use some of the magic that you're developing here to, if it takes 12 weeks to learn to fly an airplane, can we learn it in 6? I know learning and connectivity is all part of your portfolio there, but any interesting just learning related stuff that you can mention on potential applications to these tools? Obviously, you got all the diseases that we just ran through that you're going to be focusing on, but anything that can teach me calculus in 5 weeks or medicine in a year or anything else. Love to have that.
I don't think so. I think we're not, I don't think we're there. I think our knowledge of how we learn, how we memorize, and how we socialize, and many of these aspects are, in a very, very preliminary stages. I think right now we are just learning the circuit underlying the learning, and the question of can we learn much faster? I think these are all very intriguing questions that we are very, very far from a good answer. And my project on learning had to do with very, very small animals and very, very preliminary work. And then I think the kind of animal models that we used to understand learning has been very, very primitive. The animal had like a couple of thousand neurons. And I think when you compare that to humans, we have billions of neurons. And then what percentage of our neurons as humans are focused on learning? I mean, that is interesting question, but we are very, very far from understanding. And one of my colleagues from University of Washington said something interesting that sticks with me. He was saying something like, many years ago, when it comes to brain, we didn't know what we don't know.
Mm.
And fast forward 30, 40 years, now we know what we don't know. I think is an interesting concept. I don't know whether that was his saying or he got it from somebody else, but I think it's intriguing. I think that is very true. Right now, we may know what we don't know. I think that we don't know how we learn. And if we figure out how we learn, and then maybe in 50 years we can speed up our knowledge of our learning of calculus from years to weeks. We don't know. And right now we have so many challenges to focus on. I think the concept of learning and memory and many of these issues are going to be there. And it's just a big challenge. That's all.
Understood. What else is hot for 2023? I mean, I noticed that recently there was this RICE Neuroengineering conference, Interface RICE, that you were involved in setting up. Any other conferences, talks, public-facing stuff that you're going to be doing in the coming months, places that we can listen to you, possibly meet you? Anything else hot on the calendar that's please?
We would love to invite you to come to our next year's conference, Interface 2024, RICE Interface RICE 2024, which would be in May of this coming May. I would love to have you, because of your interest, because of your, sort of knowledge of this field. And as you could imagine, there are more and more conferences focused on neuroengineering. Yeah. As you know, over the last 50 years, there are tons of conferences focused on neuroscience, which is great. Right. And I think the engineering aspect of this problem is getting a lot of attention. And there is a conference called MHSRS, which happens in Orlando every year, and I'm going to attend that. And this is basically medical health research conference, and there's a lot of DoD and Army folks there that are focused on brain health. And I'm going to be there, and it's going to be a good conference to go take a look. There is a very high attendance conference. There are probably thousands of people who be there. And our conference, Interface RICE, is very small, only 160 people. But it's a very intimate conference that you meet everybody. And there's only one track. And you hear everything, you meet everybody, and you meet, and as I said, there'll be a whole bunch of medical doctors and neurosurgeons and all that. Therefore, and you're very close to them, and it's very different style than this conference that I mentioned, MHSRS. Very different, day and night different, but still interesting. Both of them are very interesting thing to go, and as I said, neuroengineering is getting a lot of attention. I expect to have more and more conferences focused on how engineers can help understand the brain.
Mm-hmm. Well, you just made me think of one other thing. Speaking of how hot and exciting this area has gotten, especially, there's been this guy, Musk, or I forget what his name is, but he's out there talking about brain interfaces and all that stuff quite a bit in the social media. Any interesting, I know it's early days still, but any interesting startup initiatives that are spinning out of RNI yet, or not yet? Is it a little
No, yes, there is actually. Okay. Believe it or not, let's say 4 of my colleagues already have startups.
Nice.
Already have a startup. One of them is very far along. He already raised, quite a few dollars to get the process going. And Rice has a entity called ION, ION,
Okay.
that is about a mile away from campus, and that is an incubator that
Nice.
Rice put together that basically gives opportunity and space and all startup would need to build it up, and then brings in investors on a daily basis to look at the technologies and then possibly invest. Is a brilliant idea, and it's been going on for a few years now. It was an old Sears building that were abandoned for years, and Rice purchased it and turned that into this incubator, basically.
There you go.
And one of my colleagues has a company there, and he's building it out. And then two of other colleagues of mine have similar. They're a few years behind, but they have similar ideas of taking their technologies to the market. And myself and one of my colleagues from Houston Methodist, who's a chair of neurosurgery, I haven't mentioned his name yet, but his name is Gavin Britz, a brilliant neurosurgeon. And the two of us have this idea of putting together a company around the concept of brain health, which is kind of related to glymphatic flow.
Yep.
And again, we have this idea to take this concept to the market. And as you know, there's a long way. It's not a overnight thing. And right now we are in the phase of talking to lawyers and then filing patents and all that. And
Well,
I think is a very natural step.
Absolutely. No, that's why I wanted to bring it up. Now, obviously, not just for the the private sector angle, but the fact that the connection to the basic science. It's such a premier institute. I think it's just so exciting, and I just again I thank you for taking the time to come on and talk us through these projects. I know I've been bothering you for a couple of years now, but this was wonderful, and just really wishing you and the team there the best with all of it as you proceed with these technologies in 2023 and beyond. Again, for everybody that's going to be listening to this particular show across the various podcast networks or watching it on our YouTube channel. Again, you've been listening to Dr. Behnaam Aazhang, J.S. Abercrombie Professor, Electrical and Computer Engineering, Director of the Rice Neuroengineering Initiative, Rice University. Behnaam, I want to again thank you for taking the time out of your schedule. Obviously, thank you for everything you're doing there. And as we like to say on our show, thanks for creating a much better tomorrow for all of us via what you do. Really a great story. Thank you. Thanks for having me on the show. I hope that I conveyed my excitement, like a childish type excitement. I feel the same. That's how I feel. Absolutely. It's great seeing you. Thank you so much.